All right, so let's move through the extrinsic. Now, there's one thing to note in particular about this extrinsic. We don't mind whether it's being signed by validators from kappa or lambda. Now, if you remember, kappa is the current validator set, right? It's the keys of the current validators. Lambda are the keys of the previous validators. There's a reason that we essentially want to allow for the possibility that the last validator sets are issuing, last validators, so validators from the previous epoch, are issuing judgments in the current epoch. We don't want to, otherwise there could be an attack where you basically put forward an invalid work report at the very end of an epoch and delay, spam validators, or in other ways delay a report from happening. Good. Now we talk about culprits. Culprits are those misbehaving validators. So, what do we have? We also talk about validators at fault, F. So culprits are the two guarantors that in the case of an invalid work report were the ones that said it was valid, right? The two guarantors, or possibly three, that brought it onto the chain. They're called culprits. They're very bad. Faults are the validators that issued an invalid judgment. They're kind of equally bad, but we have to report them differently because of different kinds of signatures that we're checking. So our extrinsic has three fields. The first one is just the judgments, which is basically, here is what I think about this work report as a validator. The second are proofs that a particular guarantor was responsible for a particular work report. And the third are faults, which is basically that are those who did audits, those who issued judgments that were invalid, or that were in contradiction to what we now believe with some certainty was the validity of a work report. All right, so let's look at this equation. What's J? Well, let's start with C and F because they're easy. So C is a tuple with a hash. In this case, it's the hash of the work report. Oh dear, this E is wrong. This should be a blackboard E. Okay, hash of the work report, hash of the in fact, the ED 25519 key of the validator, and an ED 25519 signature. Okay, these two. This one has the same because, in fact, you just need the same information. The signature will be on a different thing. That's the thing, right? So with C, it's a guarantor signature, and it's got the guarantor signature payload, message payload. With F, it's a judgment signature. It's got a judgments payload. Yep. All right, let's look at J. So J is a sequence, right? In the sequence, there's a bunch of tuples. In each tuple, there's a hash of the work report. Then there is this funny thing here. Let's break this down. So, firstly, we're subtracting a set. When we do this, this is notation introduced in the first chapter. When we subtract a set, we're basically saying it's a set. But from every item, we're going to sort of add this and subtract this. So in this case, it's the set 0, 1. Right? And then we're going to basically take our current time, prior, divide it by the epoch length to get our current epoch, and that's our current epoch index, right? This term here. And then we're going to subtract either 1 or 0, and we're going to end up with a set of two items, which is the current epoch and the previous epoch. Yeah? All right, good. So this middle term in the tuple is basically telling us which validator set, whether it's kappa or lambda, to expect. Yeah? And we're going to either have the keys of kappa if it's our current epoch, or lambda if it's the epoch -1. Yep? Okay. Finally, we have our judgment signature set. It's a sequence, and we're looking for the floor of 2/3 of the validators plus 1. Yeah, so it's a usual 2/3 plus 1 signatures. Each signature, well, we've got the actual signature, that's the final item in the tuple. We also want to know the validator index in kappa or lambda. We don't know which one. I mean, we know which one from this middle term, but this one gives the NV, this validator index, gives us the actual index into that sequence. And then also this Boolean true or false, yeah, which is, we can fudge it and just say it's 0 or 1. That's how it gets serialized. All right, and so what this J thing does is it basically says, right, every judgment, it's kind of more like a verdict than a judgment, but like every work report of which we have a judgment on or a verdict of is going to have the hash. It's going to be an item in this J. It's going to be the work report hash to identify what work report we're talking about, which set of validators it is, current block or last block, and current epoch or last epoch, and all of the signatures, of which by all we mean 2/3 plus 1. Now we actually mean exactly 2/3 plus 1, right? There's no colon before, there's no colon after. You can't have more than 2/3 plus 1, you can't have less than 2/3 plus 1. It's exactly 2/3 plus 1. Why, we're going to see in a second. All right, so each judgment in J implies at least 2 items on the same report hash. Oh, no, it doesn't. Ah, yes, it does. Okay. At least 2 times the same report. Yes. So each judgment in J implies at least 2 items of the same report hash in the sequence of culprits C and at least 1 item faults F. It actually doesn't require this last bit. It will generally have the last bit, but it might not. It does require, it does imply 2 items with the same report hash in the sequence of culprits. What I mean by this is that we must have, for any judgment, 2 items in C. For any item in J, we need 2 items in C. Why? Because when there is a judgment, there will always have been 2 validators. Yeah? In fact, this isn't an and here, this is an or. Yeah? And this should say or, at least. Why? Well, because if it's a positive judgment, then there won't be any guarantors responsible for it because, of course, they will have been in the right. They will have been totally right in guaranteeing it. But if there's a positive judgment, it must have been issued by a dispute, right? By a negative audit. That's the only reason that you're going to get 2/3 plus 1 validators to bother actually going through and evaluating a work report, work package. And so if it's a positive judgment, there is going to be at least 1 validator at fault, F. Yeah? So you're either going to have 1 validator at fault, or you're going to have at least 2 that are culprits, that are bad guarantors. There's going to be either at least one bad auditor, or at least 2 bad guarantors, for us to bother, having 2/3 plus 1 validators audit something. Like, this is a big deal when 2/3 plus 1 audit the same work package. It's not something that we want to do very often, and so we're going to make sure we're going to slash at least one validator. So that's what we're saying here. All judgment signatures must be valid in terms of one of the 2 allocated allowed validator sets, right? Kappa or lambda. It's identified by the second term, as I mentioned. So what we're looking at here is for all of these report hashes, I think A is age, right? So it's like the epoch, and V is the validator signatures. So for all of these in J, and then for all of the validator signatures, validator index, verdict, validator index, and signature, the signature has to be in this set of signatures, right? Which we do by denoting the validator key, or the signing key. In this case, it's K, bold K, indexed by I. I is the validator index, if you remember, and then this E here should actually be capital E, and that's the ED 2551 key. Okay, and then what is it that we're signing? The message. It's this X V, which is going to be either jam valid or jam invalid, depending on the verdict. And it's concatenated with R, the report hash. Okay, pretty simple, I would say. That one, not too many surprises. K here, bold K, is going to be either kappa or lambda, depending on whether our age is the current epoch or the last epoch. Yep. All right, so that's all that's saying is let's check these signatures. Now, we've got the culprit and fault signatures. Culprit, fault. Now they're both report hash, report hash signature and key. I think that is it? Yes, key. So, report hash, that's going to be that must be a member of either this ban set, so basically this uncertain set, or the wrong, the corrupt set. Yeah. So we either have to be certain that we can't know, or certain that it's wrong. And if it's in either of these situations, and if our key is in lambda or kappa, subtracted from who's already been punished. We don't care about having the same key reported multiple times. And if the signature is the ED 2519 signature for K, the key, and they have guaranteed the work report. Yeah. So what we're looking for here is a guarantor signature of the work report R that has not yet been punished, and that the work report is in one of these two sets. This may, watch out in a future revision, this may change to just phi C, yeah? But for now we'll leave it as phi beta or phi C, phi B or phi C. Okay, now for F, fault, we're looking for the work report to be in phi prime, actually. So we're looking for what happens after the judgments have been evaluated, yeah? Phi prime A or phi prime C, and basically the same stuff, except we're looking for the this message to not just be the work report hash, but the so the message context is now going to be one of two contexts. It's either going to be jam invalid or jam valid, but if you notice here, we're looking for a signature that disagrees with whether it was valid. Yeah, by saying it must be in this phi prime C, we're basically saying we're looking for the opposite of the two messages that we should be having. Yeah, because if it's in C, it's bad, but if it's true, it's jam valid, right? So it's like if it's in C, it's like we know it's bad, but yet they said it's valid. Similarly, if it's not in C, then it's definitely valid because it's in A, because we said here it must be in either A or C, but yet false means that it will be the invalid message. So this is just a very simple way of saying they voted the wrong way. Yeah? All right, good. Everything is ordered. The main reason it's ordered is to make implementers' lives easier. This way you don't have to check to see whether there are duplicates in there. You just make sure that it's different to the last one and that it's ordered correctly as you're going through it, which makes it a very simple linear operation rather than actually having to specifically go through and look out for duplicates in the block execution. But it does mean that for block producers is just a simple sort operation after you've put together all the extrinsics. So judgments J are ordered by report hash. I'm not going to have the same, obviously not going to have two different judgments on the same report hash, so they have to be unique. Culprit signatures C and F also ordered by culprit identity. Can't have the same culprit identity with different sort of culprit and fault reports. So they're also going to be unique. No duplicate report hashes, da, da, da. Okay. So this is our very simple shorthand for saying that they must be unique and in order. So we take, it's the sequence of all of these tuples in J, the judgments, but we're ordering and getting rid of non-unique, getting rid of duplicates, and we're ordering by R. Right, and that's basically what this bit means. So it's J must equal J after it's been ordered and had duplicates removed, which basically means it must already have been ordered and have duplicates removed. Same thing goes for C, same thing goes for F. This little formula here basically says, right, the set of all of the reports that are in, that we have a judgment on, must be, what's it called, disjoint with the sets of reports that have already been reported. This should include C as well. C was a recently added thing, which is why it's a little bit iffy. It's still in draft, but yeah. So A, B, and C, put them all together, and we can't have judgments on those, right? Because they've already been judged. We don't want to be wasting the system's time with judging them again. Plus, we may end up with a situation of, you know, if mummy says no, go ask daddy, yeah? We don't, once we've made a judgment, we just have to assume that it's valid. Otherwise, there's some incentive to keep asking for judgments. This is especially the case on different forks. There's a lot of subtlety here. I don't have time to go into all the subtlety, and I probably don't have the depth of understanding to go into all the subtlety, but there is a lot of subtlety, and it's been audited for Polkadot, and it was, a lot of it was introduced specifically for these cases where things are on different forks, basically. Most of the attacks in elves are based on having different forks, and pre-mining one fork, and pre-constructing one fork, and then with enough validators, and then switching over in case you're caught. Yeah. So there's a lot of subtlety to ensure that that isn't a possible attack vector. All right. Now, for all of these judgment reports, we're looking to essentially say they're ordered by validator index, right? So all of these signatures in the judgment reports, all the judgments basically, are ordered by validator index. Very simple. Now we make a, we're going to define a term J, this bold J here. And it's a convenience term. We're going to use it in a few of the other places. I think we might even see it later tonight. And it basically means the sequence of work reports that have been judged. It's, in fact, work reports and the number of valid judgments from the validators. So N, in this case, is going to be either, oh, in fact, we put it down here. So for all of these pairs in here, all R's and T's in J, T is going to be either, it's going to be 0 or a floor of a third V, or floor of 2/3 V plus 1. Okay, and this is like how many sort of votes for validity that the work report got. Yeah. Either these actually, it's sort of trimodal. Yeah, and this basically corresponds to whether we believe the work report is invalid, valid, or we cannot know whether it is invalid or valid. Yeah. The game theoretics works out, but basically there should be no instance, assuming that 2/3 of the nodes are online and honest, where it can be anything other than these. Yeah, where these are not a possibility. We don't really care what the other 1/3 v minus 1 are voting, in essence. We only care about 2/3 plus one of them. And they should generally vote the same way, unless there's some really weird stuff happening and different client implementations are doing different things, in which case we'll have this middle thing and we basically just say, we don't know, but we're going to get rid of it from the chain but not punish anymore. Okay. So what does J, what's J about? Well, basically we're going to take our judgments, keeping the same order. We're going to go through every item and we're going to take R, the report hash, and then we're just going to sum up the verdicts. And because we know that the verdict is either 0 or 1 for each of these judgments, right? We're just going to add them up. And if it's 0, it'll just add in 0. If it's 1, it will add in a 1. So we're going to end up, because we know that there's 2/3 plus 1 of these sort of signatures, we're going to end up with somewhere between 0 and 2/3 plus 1. And what we're asserting is that, well, it can either be 0, 2/3 plus 1, or a third V, right? So it's going to either be no one thinks it's valid, everyone thinks it's valid, or a smaller half think it's valid. Almost half think it's valid. Right. Fine. Yep.
Like when there's like more than 1/3 voting on validity, like voting that it's valid but not 2/3 plus 1, then it would just take the calculator, would discard the additional.
Yep, they'll select a third from one set and a third plus 1 from the other set. And the way that it works out is that they, assuming that everyone votes, which is the assumption, we're going to end up with somewhere in here. Like if it's valid, we assume that we will be able to get 2/3 plus 1 invalid votes. Votes for invalidity. This is part of the security assumptions. If it's invalid, we'll get 2/3 plus 1 votes for invalidity. If it is valid, we assume that we assume that we will get 2/3 plus 1 votes for validity. We may get a third minus 1 votes for invalidity as well, but that will be a third minus 1, yeah? Which means no one can report that as being uncertain, because there'll be 1 vote short, yeah? Because our 2/3 plus 1 is the threshold that we believe we will always get. If we ever end up with a third voting like that it's valid, then something's and everyone else thinking it's invalid, something is really screwy, yeah? Okay. Right, so let's move into 110. So for all of the cores, going through all the cores, we're going to, we're making this new intermediate state, row dagger, this thing here. This is basically row dagger, right? There's nothing else to it. I think row has the prior row dagger, maybe row double dagger, and then row prime, which is the posterior row. Row is what all of the cores are doing right now. It's essentially what work packages they should be making available. Yeah, it kind of doubles up in meaning. So it's like when a work report comes on chain, it goes into row, and then it stays in row until either it's timed out or it becomes available. What we're going to do is say, right, well, anything that's in row, we're going to remove if we now know it's invalid or might be invalid, unless we're certain that it's valid or no dispute has arose, we're going to remove it. And that's what this is doing. So basically, we remove the item if the item is in the judgments and we're not certain. The 2/3 V, T being 2/3 V implies certainty. If T is not 2/3 V, this could just as easily be not equal, right? But if T is not, or if T is less than 2/3 V, then it means that we are not certain that it's valid. We're either certain it's invalid or not certain at all. In which case, we don't want it accumulated. Yeah, we've got to get it out before it gets accumulated and potentially corrupt state. And that's what we're doing here. So row, the core, basically if the core's work report with T is in the judgment, then get rid of it. T is as I say, this threshold. It was not so easy to write, the core's work report and anything but 2/3 V, which is what I meant. But this is basically saying that if it's the core's work report and either 0 or 1/3 V, then get rid of it. Okay. Good. Now we have our just typical, pretty straightforward state updates. This is basically just adding things into each of these sets according to the set semantics. So your A, B, C, and P, we're adding for A all of the things that all of the judgments where with 2/3 plus 1 think it's valid, because now this is enough for us to say definitely valid. So that goes into A. For B, it's all of the ones we're uncertain about, so it's basically where there's a third valid. That goes into B. B should rarely be used, right? It should be a crazy thing for there to be a third of validators that think something is valid and everyone else not to. Very, very crazy. So this is sort of a bit territory here that we never really want to see, but it might happen, so we have to handle it. C is where we know it's invalid. No one is voting for this being valid, apart from the original guarantors, of course, and so that goes into our corrupt set. And then finally, the punish set is all of these keys that are either in C or F. We don't make a distinction at this stage. This is something that might possibly change in later editions, depending on whether we believe we need to distinguish between the guarantors who were bad and the auditors that were bad. But at the moment, I don't really see any big need.